Here we are on lecture 3. You remember last time we were discussing the complexity of this problem, minimizing over all polynomials p, whose one norm is bounded by t of the absolute value, the expectation x, and f is a fixed function. And I claimed that this optimization problem can be approximately solved using a projected version of gradient descent. This could be done. So this can be solved. In time polynomial in n and 1 over epsilon and t. Epsilon here is your error parameter. And this allows you to agnostically learn sparse polynomials. What I wanted to do today, so this result is somewhat involved, and I wanted to describe at a fairly high level how to solve this problem using boosting. And I wanted to emphasize, you'll see when we get to agnostic boosting, because we're working in the agnostic model, that there are some really nice advantages to doing boosting, combining boosting with the agnostic model. It's another reason why I sort of really like the agnostic model of learning. Okay, so let me remind you what is boosting. So again, imagine you have access. The learner has access to f, and there's no noise. Let's think about the noiseless case. And the goal, of course, is to output h such that the probability that h does not equal f is at most epsilon. Instead, I'm going to describe the weak learning assumption. And I'm going to assume that that we only have a learner that can output a hypothesis that is, say, 51% accurate. So here gamma would be 1%. This being able to come up with an epsilon accurate hypothesis, this is often referred to as strong learning. And if you're only able to come up with a hypothesis that has accuracy 51%, we call this weak learning. And a major result of Rob Shapiri was that if there exists a weak learner that succeeds with respect to all distributions D, this implies that there exists a strong learner that succeeds with respect to all distributions. Okay, so remember here we were sort of interested in learning just with respect to the uniform distribution. Okay, and what I'm claiming boosting will accomplish is that it will take a weak learner, but the weak learner has to succeed with respect to all distributions. And then if you have a weak learner that can succeed with respect to all distributions, you'll get a strong learner that succeeds with respect to all distributions. So already there's sort of a disconnect between what we want to do, that is, learn with respect to one kind of fixed distribution. And here I'm claiming boosting works with respect to all distributions, but we'll address that point in a moment, and we'll work around it here. So this reduction is called a boosting algorithm. So a boosting algorithm is this reduction. And very roughly, at a very, very high level, what will happen is the boosting algorithm will run the weak learner. It will receive a hypothesis that's correct. Say these examples, it'll draw a bunch of examples, it'll have a hypothesis that's correct here and it's incorrect here. The boosting algorithm will create a new distribution that puts more weight on these points and less weight on these points. It'll run the weak learning algorithm again to obtain another hypothesis. It will then modify the distribution again, and so on and so forth. And then at the end, it will take a majority of these weak hypotheses in order to obtain a strong hypothesis. So let me actually give you an example of a boosting algorithm that you probably haven't seen and prove to you that it works. It has some interesting properties. This is called, so let me show you something called boosting by branching programs. This is by Phil Long and Rocco Servideo. And the reason why I'm going to show you this boosting algorithm is, one, you probably haven't seen it before, and two, it's conceptually very simple, and it actually has a fairly simple proof. Okay. So remember, we're going to assume that, so let's fix a concept class C and some C in that concept that you're trying to learn. Again, there's no noise here. And then we'll assume that there exists a weak learner such that for every distribution, given random examples, x, C of x, and this is chosen according to D, the weak learner outputs H such that the probability of x. Now I'm going to make a slightly stronger weak learning assumption. I'm going to assume that all examples drawn from the positive part of D, we have H of x equals C of x, at least 1/2 plus gamma. And for all of the examples drawn from the negative part of D, so D plus is the set of all positively labeled random examples. D minus is the set of all randomly labeled examples. So you can see, I mean, a priori, it looks like I'm making a stronger assumption on the weak learner. I mean, you could imagine a distribution that has very few negative examples and a successful weak learner that gets nothing right on D minus, but it's very successful on D plus. Here it looks like I'm assuming something stronger, but in fact, this turns out to be equivalent to the original, just the standard plain weak learning assumption. And this equivalence is an exercise. It's not difficult.
By answering yes without looking at the input with some probability.
Yeah, something like that. Yes. Okay, so the algorithm, maybe I'll draw it over here. The first thing the boosting algorithm is going to do is draw a branching program. Well, I guess, strictly speaking, it's just drawing a graph at this point. And it's going to do this for t levels, capital T. Okay, this isn't very exciting. So I guess we'll get down here to t levels. And then at the leaves, it'll place -1, -1, -1, -1, until we get to index t over 2. Then it'll start placing +1s, 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 +1s. Okay. So the boosting algorithm works as follows. First, it runs the weak learner to obtain H0. And it places H0 at the root of this branching program. Then it's going to draw a sufficiently large set of new labeled examples. And for each one of these new labeled examples, so H0, on some of these new examples, H0 may label them minus. And on some of these new randomly labeled examples, H0 may say plus. So the randomly chosen examples that H0 labels minus will induce a new distribution on examples. Okay, you randomly choose some examples, and you move to the left if H0 labels you -1. Also, from these randomly chosen examples, some of them will move to the right if H0 says +1. So this will correspond to 2. So now we've induced 2 new distributions.
So is it the one distribution is just the original distribution conditioned on H0 answering plus?
Correct.
Uh-huh.
Yep, good. So D01 is original distribution conditioned on H0 equaling 0. And this is original distribution H1 saying plus. Okay.
What does the indexing mean?
Right. So so the index of the ith vertex at level t is I. So I really mean, you go down to level little t. This has index 0, this has index 1, this has index 2, this has index 3.
Okay, so that should have been D00.
Oh, thanks. Sorry.
One of the indices.
So this should be D0 is the original distribution. This should be D10 and this should be D1.
The first one is.
The first one measures what level of what level you're in.
Is the output.
The second bit is the index where you are inside that level. Yes.
Yeah. Yes. Uh-huh.
So we'll induce 2 new distributions and we'll run the weak learner 2 more times to get H10 and H11. Okay? I mean, the weak learner works with respect to every distribution. In particular, it will work with this conditional distribution and this conditional distribution. Okay. And then I'm going to continue. So here I will have distribution D20, distribution D21, distribution D22. So I'll draw a new sequence of examples. I'll look at all of the examples that end up here. That's some new distribution D20. Then I'll, so I'm drawing a sufficiently large sample of examples. Whatever examples appear here, this corresponds to some new distribution on examples. Maybe a bizarre distribution, but some distribution. This is also some distribution on examples. Okay. So I could run the weak learner again. I'll get H20, H21, H22. And I'll just continue to do this. Okay? If I'm at some node in my branching program, and I've taken a sufficiently large sequence of examples, and none of them reach this node, then I'll just ignore it. I'll chop it off from the branching program. It's not going to be relevant. And looking ahead, I'm going to choose t to be order log 1 over epsilon over gamma squared. Okay?
You have delta. What is epsilon and what is gamma? Oh, sorry.
No, I have gamma.
This is gamma, not
And
delta.
epsilon
Okay.
is going to be your final accuracy of the.
Okay.
Okay. So this is the So this is really the output hypothesis. This is your combined strong learner. If you have a new example, and you want to know how to classify this new example, you just take the path in the branching program according to all of the hypotheses labeled at each interior vertex. And if you end up on the right-hand side here, you say +1. If you end up on the left-hand side, you say -1. Okay, so let's pick a random x from the positive part of the distribution. And let's let y sub t be the index at level t that x, where x ends up. Okay, so x is a random draw from the positive part of the distribution, and y sub t is a random variable corresponding to the index at level t where x ends up. And I want to say that it's clear that the expectation of y sub capital T is exactly t over 2 plus gamma t. This is just by linearity of expectation. You could set up an indicator random variable that at level I is 1 if you move to the right and 0 if you move to the left. And by the weak learning hypothesis, for a random draw from D+, the probability when you just locally look at any one of these nodes in the branching program that you move to the right and you're positive is 1/2 plus gamma, because that's the correct direction. And similarly, if x is a negative example, then the expectation of yt is t over 2 minus gamma t. Okay, so intuitively, this branching program, when you pick a new random x, this example is going to do a biased random walk inside your branching program. And hopefully, sort of the bias pushes you towards one side if you're positive and negative towards the other side if you're negative. Okay, yeah, simple. But remember, we wanted to say that, so if h, we want the probability when x is drawn from D+, that h of x says +1, we want this to be at least 1 minus epsilon. Okay, so we want a statement, we want to say with high probability, this branching program is going to correctly label x from D plus. Okay? And the problem here, the reason why you can't use kind of a standard, say, Chernoff bound, is that the event that H21 pushes you in the right direction, why should that be independent from the event that H11 pushed you in the right direction or the wrong direction? I mean, these may not be independent events. These HIs may be very correlated. Yeah.
But the probability of going to the right, conditioned on having arrived at this vertex, is still 1/2 plus gamma, right?
Correct.
Because we set it up that we learn exactly with respect to that conditional.
Yeah, but that doesn't mean that.
That doesn't mean that it's independent.
It doesn't mean that it's independent. So
It sounds good already.
moving towards this high probability statement is not immediately clear.
Mm-hmm.
So what can we do here?
Martingale.
Yeah, it's a martingale. Right. So the expectation of yt, if this is your index at level little t, given yt minus 1, is equal to yt minus 1 plus 1/2 plus gamma. So if I create this new random variable zt, which equals yt minus some offset, you can calculate that the expectation of zt given zt minus 1 is exactly zt minus 1. And furthermore, since you're only moving at most 1 to the right or 1 to the left at every level of the branching program, you have that zt minus 1 is at most 1. Now, strictly speaking, what we want to do now, if you haven't seen this before, is apply Zuma's inequality. And we'd like to say that the probability that zt yeah. I guess this is a positive example. So the probability that this is less than t over 2 is post epsilon.
You need some margin, right? Like t over 2 minus some.
Yeah, but I've already like subtracted off my an offset here
Yeah,
to
so
kind
you
of
want to
compensate it.
that zt. Wait. Yeah. So now you know.
You want this to be less than this is 0 or something like that. I mean, I'm subtracting off this particular offset.
Yeah. So you want to estimate the
No, this
probability
can't be
that
right.
it's greater than t times gamma.
Yeah, you're right. You're right. Right, because only if it's in expectation your t over 2 plus gamma
Plus or
t.
minus gamma.
So the only way that things go wrong is that if you end up deviating by more than gamma t from your expectation. That's the only way things go wrong. Now, strictly speaking, if you want to apply a Zuma's inequality, I should have conditioned on zt the entire history, so on and so forth. But because we're in a situation where yt is actually the sum of 0, 1 indicator random variables from this branching program, it's sort of well known that I really, in this particular case, only need to condition on zt minus 1. Okay, so there's some slightly delicate issue about when, can I apply a Zuma's inequality? I mean, strictly speaking, typically you need to condition on the whole history, but In this particular case, because I'm looking at a sum of 0, 1 indicator random variables, it's actually, everything is okay. And Daniel, do you want to say something?
No, yeah. Thanks.
Okay. So we've chosen capital T precisely to be large enough so that when you plug it into a Zuma's inequality, this is exactly the bound that comes out. Yeah.
I'm slightly confused. So I understand that, for example, D10 is the distribution conditioned on the first classifier moving left. So what is D21? Is it kind of conditioned on first moving left and right, or first moving right and left?
Yeah, it's complicated to say in words. I mean, it's really...
It's just conditioned on arriving at this vertex.
It's conditioned on arriving at this vertex.
Yeah.
There's no kind of simple way to say it. And it gets even worse as you have larger depth.
Yeah, okay.
But I think conceptually this is it's simple to see what's going on here, and the proof really is just using a martingale.
As long as you just care about constant gammas, you could have done it with a real tree, I guess.
Yeah, exactly. If you wanted to build an entire binary tree and gamma is a constant, you would be all right.
Then it would be a strict Zuma.
Then it would be a strict Zuma, right, because each path is unique.
Yeah.
But we definitely want to think of gamma as being subconstant. So that's typical, yeah. I mean, we want it to be possibly inversely polynomial smalls. Okay, so this was sort of an aside into boosting. And now I want to talk about agnostic boosting. So you might recall that, again, we're interested in this minimization problem. And we said yesterday, and I maybe even mentioned the day, we said yesterday that the sparse algorithm, the KM sparse algorithm that we described on day 1, actually will output a hypothesis with error something like 8 times opt plus epsilon. You have to, the whole point here is you have to work much harder. That's what we're doing to get rid of this 8. But in some sense, you might interpret this result as a weak agnostic learning algorithm. It is getting you some factor times opt. And so why not apply some boosting type algorithm to get rid of this 8? Okay. So that's sort of precisely what I'm going to claim you can do. There were 2 kind of concurrent results, one by Kalai and Kanade, and one by Vitali Feldman, that give kind of agnostic boosting algorithms and can be used to take this as your weak learner, use it as a black box, and obtain a strong agnostic learner, one that gets exactly 1 times opt plus epsilon. And I'm going to describe sort of the key idea in these boosting algorithms that lets us succeed. But first, I need to describe the new weak learning assumption. So it's an agnostic weak learning assumption. So I'm going to fix, again, a concept class C. Say, I'm going to fix a distribution D, again, a joint distribution. And then we'll fix a concept class C. And we'll define the correlation of C with respect to D to be the max over all C and C of the expectation when xy is drawn from D of C of x times y. Okay, so this is the correlation of the most correlated concept from C. I mean, it may be very low depending on what D is, but I'm just going to refer to it as this quantity. Contrast this with the opt quantity that corresponded to error. This one's corresponding to correlation. And the weak agnostic learning assumption for C with respect to D is that we can output a hypothesis given random examples from D with correlation, so the hypothesis H, with correlation equal to gamma times core of CD minus epsilon 0. So I guess I should, sorry, the gamma epsilon 0 weak agnostic learning assumption is that we can output a hypothesis H where its correlation is a factor of gamma times the optimal minus some additive epsilon 0. Okay, so you can start to see how this KM algorithm might fit into this framework. And then the theorem, again, this is Kalai, Kanaday, Feldman, is that the weak agnostic learning is, so a gamma epsilon weak agnostic learner can be converted into an algorithm that outputs H such that probability x y is chosen from D, that H of x is not equal y, is at most opt plus epsilon 0 over gamma plus epsilon. And it runs in time poly and 1 over epsilon. Okay, so given the weak learning assumption of this nature, assuming that the weak learner is able to make epsilon 0 smaller than gamma, you can really get a very strong hypothesis that works opt plus epsilon 0 over gamma plus epsilon. At this point, you might say, well, why aren't we done? We'll take this weak agnostic learner, we'll apply this theorem, and we're done. We're in great shape. The reason why we're not done is that if you recall from the previous boosting algorithm, how do boosting algorithms work? They're changing the distribution that you start from by a little bit, and then they're running the weak learning algorithm. Remember, the original, we had this weak learning assumption that you could weakly learn with respect to all distributions. We needed a weak learner that worked with respect to all distributions. And we have this KM algorithm, and it works, but only with respect to the uniform distribution. Okay, so as soon as my boosting procedure begins to change the distribution, I'm shot. I'm in big trouble. And the remarkable property of these algorithms is that they do not change the underlying distribution. Okay, so you get a pretty amazing consequence, that is, if you have an agnostic weak learner with respect to one distribution, I can boost its accuracy with respect to that same distribution. I don't need to change the distribution. So let's see if you guys can figure out what the trick is. So just at a very high level, remember, you run the weak learner, you get a hypothesis. It's correct here. It's incorrect here. And the new distribution was formed. Remember, we want the weak learner, we want to come up with a distribution where the weak learner is forced to do better on this part of the examples. And so we increase their weight, and we decrease the weight of these examples, and that forces the weak learner to do better on this part. Now, we're in the agnostic setting. That's sort of a hint. What can the boosting algorithm do? How can it change this set of examples that we've chosen without changing the weight on any of the examples and still run the weak learner and force it to do better on this part where we were incorrect?
We put in wrong answers.
Yeah, on these points that we got correct,
yes,
we flip coins. So, you know, we're going to flip a coin for its label. We're going to change the labels by flipping coins. Now, since I've flipped coins on a bunch of these examples that I previously had gotten correct, it's completely random on this part of the distribution. So there's no accurate hypothesis on this part of the distribution. I mean, nothing can do well here. It's random. So that's going to when I run the weak learner, that's going to force it, in order to give its guarantee of what it has, it's going to force it to do better on this part of the distribution. Yeah.
Kind of on a high level, if we are not in the agnostic setting, but without any errors,
right,
without any incorrect labels, is it kind of clear that you cannot do this? You cannot kind of boost with respect to one distribution?
Yeah, I mean, well, I mean, as soon as you change even a single label in the,
this
the weak learner may fail.
This algorithm, this particular idea might fail, right?
No, I'm saying as soon as you, okay, well, if you don't change, so now we can't change labels and I can't change distributions, then I'm just going, the weak learner can just output the same hypothesis every time. I keep calling it, it gives me the same hypothesis.
Yeah.
So what can you do? So this technique is called random relabeling. And it's not quite this simple. I mean, you need to be a little careful. You need to probabilistically decide whether or not to give a coin flip to your new examples. And the probability that you do make an example, give an example a noisy label, is dependent upon how many previous hypotheses that your weak learner have given it correctly. So if most of your hypotheses during this procedure are doing well on this example, then with high probability you're going to flip a coin. You're going to make it noisy. But there are definitely some calculations to work out. So it's not simple, but it's not too difficult either, and it works. So once you have a boosting algorithm, this type of agnostic boosting algorithm, you really can combine it with these types of algorithms.
It really makes use of the fact that you can learn even if the correlation is really small or quite small.
Yes. So for example, like Nati was saying earlier, he was saying, well, this weak learning assumption that you can succeed with respect to all distributions, it's actually very, very strong. And I was saying, yeah, that's the importance of, that's why we should consider agnostic algorithms, because if you can come up with an algorithm and it succeeds in the agnostic scenario, you get this very powerful boosting for free. You don't need to succeed with respect to all distributions. Now you could say, oh, well, coming up with an agnostic learning algorithm is very hard. I would say yes, but notice these algorithms from even 20 years ago happen to have some reasonable agnostic properties, so we should really be shooting for that. Okay, so you really can combine this tool with the KM algorithm as a black box, and you will get opt plus epsilon. Okay, so So that ends kind of a unit on learning with sort of the unit on learning of noise that I wanted to talk about. I will talk about random classification noise probably tomorrow, but more in the context of hardness results and reductions. And what I want to talk about now, I want to move on to learning geometric concepts. Okay, so at the beginning of this mini course, we talked about learning decision trees, in part because that's what a lot of people in data mining do. They try and find a decision tree that is consistent or reasonably consistent with the data set. Another common thing that applied machine learning people or data mining people do is they'll take a sequence of random examples. They'll view these labeled examples as points in Rn. And they'll see if they can find a hyperplane that puts most of the positive points on one side and most of the negative points on another side. And then if you need to classify a new point that's randomly chosen, you just see which side of the hyperplane it's on. If it's on this side, you'll label it negative. If it's on this side, you'll label it positive. And if you've ever heard of a support vector machine, which is a commonly used tool in machine learning, inside of that algorithm, at the core of a support vector machine, is an algorithm for finding a hyperplane that tries to get classify as many points as possible correct. So it's a very kind of simple primitive, but it's been souped up and used in very complicated ways, and it's been very useful. So naturally, we're going to be interested in what is the computational complexity of finding a good linear separator. So we're going to be interested in functions that are the sine of w dot x minus theta, where typically we'll treat the norm of w as 1, although we don't have to. This is called the threshold. The set of points that make this function positive are a half space, and this f is usually referred to as a linear threshold function. So, right. So let's say that w and theta are unknown. And you're given a sequence of labeled examples. And you'd like to learn the unknown w's and thetas. How do you do it? Much like the case with learning a parity, each one of these examples corresponds to a linear inequality. And so on and so forth. And then I can run an LP solver, find the unknown wi's. This is a polynomial. There's a polynomial time algorithm for solving a linear program. So in polynomial time, I will find a set of wi's that's consistent with all of my data. And as I said on day one, if you take a sufficiently large set of examples and you find a consistent hypothesis, then you will have learned the concept. Okay, so it's not too difficult. I should say this is, somewhat surprisingly, this wasn't written down until '89. This is Blummer, Ehrenfeucht, Hausler, and Warmuth. But this problem of learning a half space has been studied in the 50s by Bloch, Novikov, and Rosenblatt. they came up with something called the perceptron algorithm. Maybe we'll get to that. Okay, so this is great. For every distribution, we're able to learn a linear threshold function. Of course, the question that I'm interested in, the question that, for example, that predates this problem in a way that Vapnik asked, that sort of predates the PAC model is, if you're given points that, this is the agnostic problem, they're not necessarily consistent with any one particular hyperplane, but you'd still like to output a hyperplane that approximately minimizes the number of mistakes, or is the best fitting hyperplane, what is the complexity? So given arbitrarily labeled points, what's the complexity of finding the best fitting hyperplane? Unfortunately, this is a very hard problem. So for example, if your set of examples is even with the promise that it's consistent, or it's 99% consistent with a half space, NP hard output a half space that is 51% consistent. And this is a result of Guruswamy and Raghavendra, and also Feldman, Gopalan, Kot, and Panuswamy. Okay, so it's quite a difficult problem. And this is also true if the domain is Rn or if it's minus 1, 1 to the n. For both of these cases, you get NP hardness. And then you might say, well, okay, I don't care if you output an actual hyperplane. I'm okay if you output something odd, some weird geometric concept, or even a circuit that encodes some weird geometric concept, as long as the error of this hypothesis that you output is competitive with the best fitting hyperplane. And this problem is cryptographically hard. This is work with Sasha Sherstov. It's you could break lattice-based cryptosystems if you were able to solve this particular problem. So it's sort of surprisingly hard. It's sort of bad news. But these methods seem to work very well. We might wonder why, or exactly how perverse are these distributions that figure into the hardness results. So I think a natural thing to do is to consider the case, or consider cases as we have been doing, when the marginal distribution on d of x is, say, uniform on minus 1, 1 to the n, or Gaussian. So these are, two extremely commonly well-studied distributions. What can we say? So in this, what can we say if I know something about some structure on the position of the points? And what I want to show you is that in both cases, we can agnostically learn in time n to the big O of 1 over epsilon squared.
By the way, what if it's not arbitrary? What if it's just random noise?
So random classification noise?
I don't know the term.
So each label is flipped independently with some probability, then you can solve the problem. Yeah. Hopefully, maybe tomorrow we'll talk more about that. But any algorithm, so has to do with statistical queries. Any algorithm that can be learned via statistical queries, which is a type of access to the random examples is automatically noise tolerant in that sense, and this is true for this class. Okay, so not surprisingly, what I want to do, and what we've shown that you can, what suffices for agnostic learning? Well, the existence of low-degree polynomial approximators. Okay? That's what we've talked about over the last couple of days, and that's really the only tool that we have. So I guess I should say that the output, so the goal here will be to find a polynomial p of degree order 1 over epsilon squared such that the expectation of p minus sine w dot x minus theta squared is at most epsilon. And then we'll output the sine of p. Okay, as we've talked about, just keep in the back of your mind, as long as you have a polynomial approximator, you can do agnostic learning in time exponential in degree. And so this is really what we're interested in. So let's take d of x to be Gaussian on Rn. So we have the univariate Gaussian, the PDF of the univariate Gaussian, and then we'll have the n-variate Gaussian. And so I can rewrite, remember we want a p that has small expectation. I can rewrite this expectation as the integral over Rn of p minus the sine w dot x minus theta squared phi of x dx. Okay, now because we're working with the Gaussian and everything is symmetric, without loss of generality, and I'm not going to use any properties of the coordinate system here, I can assume that the optimal half space is just the sine of x1. Okay, so I can assume that w equals 1, 0, 0, 0, 0.
You have this theta.
Oh, right. So for simplicity, let's set theta to be 0. Okay. Just to make life simple. You can deal with it. Deal with it later. Now, since we've rotated everything so that w is 1, 0, 0, 0, we're left with just x1, sine of x1 sitting here. So I can really simplify this integral.
So now it's sort of a classical question, right?
Exactly. Excuse me. Right, now it's, as you say, now it's a classical problem on real approximation theory on the line. And, since you're working in L2 with the square here, and you're considering the line and the Gaussian measure, the obvious thing you want to do is to consider an orthogonal family of polynomials on the line with respect to the Gaussian. And these are called the Hermit polynomials. They're very, very well studied in classical approximation theory. And they're a sequence of univariate polynomials. I forget what x2 and x3 are. H3 and x.
X squared.
I think it's x. Yeah, I think it's minus 2 over root 2 or something like that. And they have the nice property that, well, they're orthogonal. So hi, hj, phi of x dx equals 0 if I does not equal j. And hi squared equals 1. And the other reason why I'm bringing up the Hermit polynomials is that later we're going to talk about learning general convex sets. And so we're not going to be able to simplify all of these learning problems in Rn down to the line. I mean, we got lucky that we can do that because we were trying to approximate just one half space. But in general, when we're looking at more complicated objects, we won't be able to sort of project down onto the line. And so it's good to know, this whole time we've been talking about functions that map -1, 1 to the n to -1, 1. And we've had these parity functions. These were our basis functions. And we said that every f can be written as a linear combination of these parity functions. And these f hat s's were the Fourier coefficients. Now we're looking at functions from Rn, let's say from -1, 1 to 1. And the distribution is Gaussian. And we'll only consider functions that are bounded in this sense. So their square with respect to the Gaussian measure is bounded. Then it turns out that you can write f, or I should say, you can write f as a linear combination of products of Hermit polynomials. So for every tuple of natural numbers, you'll get some product of Hermit polynomials. So for example, 1, 2, 1, 3 would be h1 of x1, h2 of x2 squared, h3 of x3, h4 of x cubed, and so on and so forth. So I can take products of Hermit polynomials, and these will be your new basis functions. Whereas when we were looking at Fourier analysis over the hypercube, your basis functions were parities, just x1, x2, x3, or x7,
Wait, why do you need the square and the third part?
I had a 2 here.
Yeah, so it's h2 is for the 2, and then you put h, right? You have h0, with the
Oh, yeah. Sorry.
It's
you're
h1
right.
of x1, h2
Yeah, sorry,
of x2,
sorry.
h1 of x3, and h3 of x4.
Sorry. Yeah. You're right. All right. Thank you. Yeah. Thanks. Right. So the analogy I'm just trying to make is that over the hypercube you can write every function as some linear combination of these monomials. With respect to the Gaussian measure in Rn, you can write every function that's bounded this way as some infinite linear combination of products of Hermit polynomials. In particular, anytime you have a family of orthogonal polynomials on the line with respect to some distribution, you can take products and you can work in a higher dimensional space. But let's finish this particular problem. So what are we trying to do? We're trying to approximate p and the sine of x1. So f, think of f now. So f corresponds to sine of x. And since we know that every f can be written as a linear combination, we're again on the line here as of Hermit polynomials, that means that f can be written as the sum from I equals 0 to infinity of ci hi of x. And we know that this is, it's equal to this. And in fact, we know that the best degree d approximation, we still have Plancherel's equation. So the best degree d approximation to f, so best degree d approximation is the sum of the first d. And we even have a formula for ci. Ci is exactly the Fourier transform. So it's sine of x times hi of x times e to the minus x squared over 2. I'm omitting the constant, dx. And the error of, so let's call this polynomial q. The error of q is the sum of the squares of the coefficients that we didn't take. Just like in the Fourier polynomial over the cube, if you take all the degree d coefficients, your error is the sum of the squares of the coefficients you didn't take. And this, this is looking pretty nice now. I mean, we need to compute the sum of the squares of these CIs, but all we have here is a sign. So I can break up this integral into minus infinity to 0, the sign will be minus 1, plus 0 to infinity, the sign will be 1. And then I'm left with hi of x times the Gaussian measure dx. But these hi of x's are concocted to work extremely well and behave very nicely with respect to the Gaussian measure. So if you, there are books on Hermit polynomials, you can certainly find a formula for this type of integral and get a bound, and that's sort of what we did. And you can prove that this quantity is order of 1 over root d. And you can so that means that this implies that you can choose d to be order of 1 over epsilon squared. Okay. So that's one proof. What I want to do next time is to show you another proof that there's a low degree polynomial approximator for a half space. What's not nice about this proof is that it's not going to generalize very easily. Say instead of trying to approximate a half space by a polynomial, you'd like to approximate, a convex set by a polynomial, the characteristic function of a convex set in high dimensions by a polynomial.
Well, you could do, I guess it won't work.
You can't project down to one dimension now.
I wanted to say that you could try to do inclusion, exclusion, right? You can.
Yeah, that's horrible.
You would probably.
Yeah. So actually, what we did after we found this proof was we went to, all of the approximation theorists that we knew, and we said, hey, we're able to actually explicitly find a bound for a single half space. We'd like to do more interesting geometric sets, and they said, well, kind of what sets do you want to approximate? And we said, convex sets. Oh, convex sets, hopeless. If you're interested in a cylinder intersected with a hyperplane and a pyramid and a simplex in 4 dimensions, I can probably do the integration for you. And that was disappointing because we wanted to really come up with a low degree approximator for arbitrary convex sets, or certainly at least the intersection of 2 hyperplanes. And although there's a beautiful, beautiful theory of approximation, it seems to be too kind of fine grain to really use for these types of problems. I mean, you can get very, very accurate bounds on the approximation degree, and that's what these approximation theorists can do. They'll give you very, very accurate bounds. But we're willing to work with, very broad estimates on what these bounds are. We don't need the tightest of bounds. And so we needed some other methodology to try and bound the degree of the polynomial that approximates these characteristic functions. And a quantity, noise stability turns out to be sort of the right thing to look at. In fact, surface area starts to be the right thing to look at. And so next time I'll talk about that. And then we'll move on to a result by Santosh Vempala on learning convex sets that uses a very interesting result from high-dimensional convex geometry. Okay, thanks.